Hello, everyone. Thanks for joining. Welcome to another TVS colloquium. Today, we have the pleasure of having with us Stephen Thorp. He will tell us about galaxy redshifts. That is, will be very important for us in doing extragalactic transients, but also about galaxy properties and so on. So please, Stephen, take it away.
Yeah. So thanks for having me. I'm not normally at this, so it's nice to be here talking to you all. And yeah, like Priscilla said, I'm going to be talking about some modeling that we've been doing for the galaxy population to enable precise photometric redshift estimation. And there will be some connections to transient host galaxies that I'll touch on at the end as well. Yeah, so photometric redshifts, you've possibly seen an animation like this before. When we have a survey like LSST, which we now luckily have data from, we only observe photometry, so we only observe integrals of the galaxy SED. And that means that all of the detailed information in that SED is summarized with just six numbers. And figuring out the redshift if you have the full spectrum is easy. If you don't, then it's a lot harder. But you can kind of see if you look at something like this, how if there was just one type of galaxy in the universe, you would probably be able to do a pretty good job at estimating the redshift just from photometry. Because as you move the whole SED to the right, as you redshift it, your galaxy will draw out a track in color versus color space or color versus magnitude space. But in reality, it's not that simple. There's a lot of different types of galaxies, so this is quite a hard inverse problem to figure out the redshift from just those six numbers, the photometry. And that's what we're trying to do. And so in large scale structure cosmology, turns out you don't need to know the redshifts of individual galaxies really well, which is not the case for transients, where you actually do really care about individual redshifts. But for large scale structure cosmology, so weak lensing or galaxy clustering, for example, what we do is we get approximate estimates of galaxy redshifts and then sort them into tomographic bins, so slices in redshift space. And if we're able to characterize well what the distribution of the true redshift distribution is for each of our tomographic bins, then it turns out we can do cosmology pretty well. And so a way of getting at these redshift distributions is to forward model the whole thing. So you start from some population distribution over true galaxies and then forward model all the way to your observations, which are photometry. And so now I'll talk through a kind of general picture of how one might set up a forward model, which will do for galaxy photometry, but in principle, you can kind of apply the same scheme to almost any problem in some sense. So, at the base of our forward model, we'll have a population distribution. And so this is an intrinsic distribution over some intrinsic properties of whatever object you're modeling. Then a random draw from that will give you a population, so a sample of intrinsic properties. Then applying some kind of physical model or physical process to that, you can translate those intrinsic properties into something more observable. And then finally applying things like noise and selection effects on top of that, then you get something that looks really like observations. And so that's our kind of general picture of what we mean by a forward model. And of course, getting that population distribution right can be very difficult. Like it can be a very complex distribution over potentially many parameters with very non-trivial correlation structure. And so something we use for that is a diffusion model, and I'll get more into some of these details a bit later. But basically, that's similar to a normalizing flow where you express your population distribution as a continuous transform of a simple base distribution like just a Gaussian blob or something. And this turns out to be a very good way of modeling difficult densities or complicated distributions, to have this kind of non-parametric representation where you're expressing the distribution as a transform of something simpler that you can understand. And then to fit a model like this to data, there's going to be free parameters potentially at all layers of this forward model, at all layers of this hierarchy. So there'll be the shape of the population distribution. There might be some free parameters in the physical process that's transferring those physical properties to observables. And then there might be free parameters in your observational processes like your noise that you don't understand. And when whatever real data you're fitting your model to, you'll only have it in that observation space. So you'll have to basically generate model observations, compare those to the real data with some kind of distance metric, and then hopefully constrain all of the different parts of this population by matching the model observations to the real observations as closely as possible. And then to put this in more galaxy language, I've changed some of the labels on these blobs, but it's the same structure. So here, our physical parameters are things like the galaxy stellar mass, the star formation rate, some parametric representation of a galaxy. Then there's going to be some kind of physics model that's going to translate that into true fluxes like an SED, like a complete SED model. And then there's going to be noise to get you to noisy fluxes or magnitudes, which is going to be your observations. And we'll be comparing this to a real photometric catalog. And if you can do this whole training procedure, and I'll get specifically into how we do this a little bit later, but if you can do this whole training procedure, then there's a lot of things you can do with the model that you've trained. So one thing you can do is you can take that population distribution, fix it, generate some SEDs, then apply like a different noise model to make predictions for a different photometric survey. So say you could train your model on the whatever the best data you have is, and then use it to make predictions for like a survey with less bands or something like that. And I'll get more into what we're doing with that later. But then also, if you can do that, then something you can do is then to your model observations, you can apply, for example, a tomographic binning procedure, whatever you're using in your real survey, to your model galaxies to create a kind of binned representation of your model galaxies. And then from that, you can basically straight away read off those redshift distributions that you care about. So that's kind of what's motivated us to be working on this forward modeling framework. But there's a lot of other angles to it besides that. And one thing that would be particularly of interest to this group, I think, is that you can kind of take off all that other stuff for generating mock data and just take that population distribution as a prior over physical parameters. And then you can use it, combine it with some likelihood and some new galaxy photometry for an individual galaxy to do parameter inference for an individual galaxy. So you can get posteriors on the redshift, posteriors on all of its physical parameters, using this learned population distribution as an informative and hopefully well-motivated prior. And that's something that I'll talk more about later. And so here's just the cartoon to kind of summarize all of that that I just talked about in a more visual way. So in our forward model, we're going to have a population distribution over physical parameters, and specifically, they're going to be the parameters of a stellar population synthesis model. So this is something similar to the prospect parameterization. Then we'll use stellar population synthesis or a emulated accelerated version of it to translate those physical parameters into model fluxes. Then applying noise and any kind of selection effects, we'll get to something that looks like data. And so in this cartoon, we're imagining that the blue point cloud is our real data that we're trying to fit, so our real galaxy survey data. And the red point cloud is our model, like our forward modeled galaxy photometry. And so here at the start of our training procedure, the model photometry doesn't look anything like the real data. And obviously, in reality, we don't actually know what the true population distribution is for the real data. But then we'll train our model, we'll try and match the model photometry to the real photometry as close as we can by adjusting all the free parameters in this chain. And then eventually, by the time we've minimized that distance between the model photometry and the real photometry, hopefully the underlying population distribution should be representing the real galaxy population. That's the aim of what we're doing. And so now I'll go into a bit more detail about the different parts of this. So to represent a single galaxy, as I said before, we're using stellar population synthesis. So this is a parametric model for a galaxy SED that gives you, it's one of the most detailed models we have for that. And it basically gives you an almost first principles recipe for building up a galaxy SED out of the different stars that were formed over the galaxy's lifetime, gas like nebula emission, dust, potentially contributions from AGN, things like that. And so that's what we use to represent one galaxy, and this gives us a 16 parameter model for a galaxy SED. And those of you who have worked with things like Prospector and FSPS, you'll know that this is really great, but it's quite slow to generate a lot of SEDs. So we speed that up using something called Speculator, which is a neural network emulator that basically learns how to translate those SPS parameters into an SED or into photometry. So it's basically learning to do what Prospector or what FSPS can do, just much faster and in a differentiable way, which is useful for optimization purposes. So that gives us one galaxy. Then we're going to need that population distribution over the SPS parameters, which is really the core of what we want to learn. We want to constrain that population distribution. And so to represent that, we use the score-based diffusion model. And so this is a model that expresses an arbitrary distribution in many dimensions as a transformation of a simple Gaussian blob. And the transformation is represented with a differential equation, either stochastic or you can have a deterministic probabilistic version of it as well. I can talk about that at the end if people are interested in that sort of thing. But it's sort of quite like a normalizing flow where you're representing your complicated density as some sort of transformation of something much simpler. Right, and so we've got our representation of the population distribution. We know what parameters we're using to represent one galaxy. We still need to translate the model photometry into something that looks like data. And there's a few different aspects to that. The most difficult one is knowing how to put realistic noise on your model fluxes. And so for that, we use, again, something non-parametric, something flexible to learn that distribution. So we learn, okay, for our galaxy survey, what's the distribution of flux errors for a given flux? And that's something we train alongside the rest of the model, because that's something that we need to learn how to do to be able to complete that forward model. So that's all of the different parts of the model. And I said, if you set up a forward model like that, you want to train it on some of the best data you have available. And the data we've been using is Cosmos 2020, which some of you might have already seen before. So this is a small patch of the sky, about 2 square degrees, that has been observed very deeply over many years with a lot of different instruments and a lot of different wavelengths. And so if you make a mid-infrared selection on this field, you get something like 420,000 galaxies up to magnitude 26 in sort of like the like 2.5 micron Spitzer band. And yeah, it's got 26 band photometry, which is really nice. So it goes from like the near UV right out to the mid infrared. And there's even some narrow bands. So this is really richly constraining data for a model like this, for a complete population model. And so our plan or our aim is to train our model on this really deep, really well observed field so we can then transfer it to other parts of the sky where there's not such rich data. So now I'll show you some results of what we get when we've trained our population model. So the first thing I'll show is this uncertainty model that I said about before. So this is learning how to add noise to the photometry. And so this in each panel here, we're showing the joint distribution of flux uncertainty versus magnitude. And that's something that the model is having to learn to be able to replicate the Cosmos data that we're training on. And so here we're comparing that to the red is showing our model after it's been trained, and the blue is showing the flux uncertainties and magnitudes reported by Cosmos itself. So we see pretty good agreement for all of these, and it even can capture some of the more complicated distributions like these vista bands where there's kind of a mixture of depths in the field. So you have different noise properties, two different sets of noise properties occurring within the field. And then this is just showing our predicted model magnitudes compared to the Cosmos data. And so we generally see pretty good agreement across the board here. One thing that's slightly tricky is so in Cosmos, although we're applying this magnitude 26 cut in Spitzer IRAC channel 1, there's actually a degree of incompleteness in the Cosmos field. So that's why the model here is continuing to rise when the Cosmos data is turning over. There's some degree of incompleteness in Cosmos at these very faint magnitudes. But we're hoping that with Cosmos 2025, which came out recently, which we're excited about, we're hoping that this will be a bit cleaner. So that will be our next model, hopefully. And then this is looking at colors. So just the distributions of colors predicted by the model. And any disagreements here are they're within the color calibration of the Cosmos data. So if you Cosmos produce their photometry in a few different ways, and if you look at the offsets in some of the colors between those different photometric extractions, there's some baseline level of variation there in some of these colors. And so the disagreements that we see here, particularly in this KS minus channel 1 color, this is kind of within the level that's expected based on the Cosmos calibration. So we're not too concerned about the fact that we look different there. And then this is just looking at the color versus color 2D plots, so we don't need to say much about that. And so once the model is trained and reproduces the photometry, we can look at that population distribution over the physical parameters at the base of it and slice it up in lots of different ways to see what the model has inferred about the galaxy population probed by Cosmos. And so one of the things, if you're a cosmologist, that you'll care about is the redshift distribution. And so this is showing here in the red curves our population level estimate of the redshift distribution in the Cosmos field subject to some selection. And so we're very happy with how these look. And once the model has all of this within it, you can apply the color selection, the selection effects from other surveys to model photometry for those surveys, and then you can extract redshift distributions using this already trained model for any other survey that you have a data model of. So something that's kind of what motivated this whole thing, really. But then aside from the redshifts, something that we can, like, we have 16 parameters in that population model, and we can kind of slice it up in any way we like and extract all kinds of different predictions and all kinds of different relations that have been constrained just from fitting the photometry in that field. So here is showing the redshift evolution of the mass metallicity relation. So in the red curves, we're showing the distribution of stellar metallicities as a function of stellar mass, and then the blue dashed lines are showing the distribution of gas phase metallicities as a function of stellar mass. And we can see just by binning up our population distribution, our learned population distribution, we can see how this evolves as a function of redshift. And we can also look at things like the fundamental metallicity relations, so how the typical gas phase metallicity evolves with stellar mass and star formation rate. And we see this expected trend of like very low metallicities along this ridge here on the left-hand side. So this is the kind of upper edge of the star forming sequence, if you will. And then also you can see this tendency for higher metallicities as a function of high stellar mass, which is what you expect again. Also, something that's interesting, if I put my former Type 1a supernova hat on, is to see how things like dust attenuation vary with galaxy properties, because that has implications for how we standardize transients or standardize Type 1a supernovae. So this is showing the model's learned distribution of diffuse dust attenuation, so galaxy-wide dust attenuation as a function of stellar mass or as a function of star formation rate. And this is about the behavior you expect, where for high star formation rates, the amount of dust rises pretty steeply. And for more massive galaxies, you get a broader distribution here. So you get more, like, the dustiest things are mostly at the higher mass end, and then you get this broader, fairly broad spread in different behaviors. And then on the right hand side here, I'm showing the star formation rate as a function of stellar mass as a function of redshift. And so this is what they call the star forming main sequence. And we see the kind of expected behavior where the lowest redshifts, this has a kind of, like, the median relation there corresponds to a specific star formation rate of around -10 per year. That's log specific star formation rate per year equals -10, which maybe is a pretty hard to interpret number now I think about it. But yeah, and then once you get to redshift 1, it kind of rises by about an order of magnitude the typical star formation rate, because that's where the star formation rate density of the universe peaks. Yeah, what have we got? And one thing that popped out when we were training this model that we didn't expect, but we found pretty interesting, is we have an AGN component in our SCD model, so we can look at where in different parts of parameter space the strongest AGN contributions are. And so here we're showing stellar mass versus redshift, and we see a kind of this specific, like, area around kind of like 10 to the 10 solar masses and redshift 1 to 2, where we see a much higher sort of median AGN activity. And this is based on dust emission in the mid-infrared, I should say. And that kind of correlates pretty well with what you expect to be the peak of black hole activity within the history of the universe, and also where feedback is expected to be the strongest. And to look at this a bit more, we looked at our star forming sequence plot. So again, that star formation rate versus mass distribution. And something that popped out is that the most star forming galaxies, so the things that are along this ridge, so the things that have the highest star formation rate for their stellar masses, those are the ones where there's a high AGN activity. And that's somewhat expected for these this AGN signature, particularly where it's re-radiated emission in the mid-infrared. You're expecting that's going to correlate with a lot of dust and gas around and very high accretion rates. And the that environment of lots of dust and gas around is favorable for both efficient AGN accretion and also for high star formation activity. So this is a trend that kind of pops out quite a lot in the literature, and we were, yeah, surprised and happy to see it appearing here too. And then a few other galaxy evolution things. I'll maybe jump over these a bit faster. So this is work from Sinan Dego, which is currently ongoing, to slice up the model and extract the star formation rate density. So the volumetric star formation rate as a function of redshift for the universe. Um, and then also Sinan's been looking at things like what makes a galaxy star forming, or how do we decide that a galaxy is star forming? And so you can, for example, look at like its estimated star formation rate from an SED fit, but you can also look at things like its rest frame colors, and people come up with different rest frame color cuts to delineate between star forming and quiescent galaxies. And so it's kind of been interesting to see what the model predicts for this once it's been trained on galaxy photometry. And we see that, yeah, the typical NUV minus R versus R minus J color cut that people use to select quiescent galaxies, those galaxies really are typically the most quiescent, although there's some non-trivial population that kind of slips over the cut. So this is something interesting that we're exploring at the moment. Um, and this is some predictions for how the fraction of quiescent galaxies evolves with redshift or evolves with stellar mass. And I'll skip that one. And so for this group, the population level stuff maybe isn't as interesting. And what will be more useful is being able to take that population model as a prior and do SED fits for individual galaxies. So you can then get posteriors on redshifts and physical parameters for individual galaxies that you care about, probably because they've got a supernova or a transient in them. And so this is something that we've been working on a bit more recently. And so here's an example SED fit to a galaxy from Cosmos under both R prior, which we're showing in red, and a kind of broader, more uniform prior, which we're showing in blue. And so having this informative prior that was trained to actually work as a population model, it gets you much tighter constraints on a lot of the SPS parameters, which can be difficult to constrain from photometry alone. And that gets you a much more precise redshift posterior, so hopefully you have a better idea of where your galaxy is. And to validate our redshift posteriors, particularly, we've been looking at spectroscopic samples. So here's showing our posterior median photometric redshifts versus spectroscopic redshift for a subset of about 10,000 galaxies that have had spectra available from the Cosmos field. And this is just, again, another SED fit and showing the redshift posterior. And then this is a slightly updated version of the same plot using a much bigger spectroscopic sample that's become available recently. and that covers a much wider redshift range. And we still see a very small scatter of our photometric redshifts relative to the spectroscopic redshifts throughout this out to redshift 6, basically, which is pretty good. And our stellar masses agree pretty well with other SED fitting codes, which is nice. And so that was all results for Cosmos. I'll show you now some results for the Kilo Degree survey, which is a much larger area survey. So this is doing the thing that I said about at the start of, okay, we're going to take our learned prior and use it to do SED fitting for galaxies with less data available. So this is just broadband photometry in this field and not quite as wide a wavelength range as Cosmos. And so this is the kind of situation where we're going to expect our having this well motivated prior to really give us some advantage. And just as a comparison, the Cosmos field that we trained our model on, it's just this little box there, basically, and kids is a much wider area. And this is work that Arnik Halder has been leading. Hopefully it will be out pretty soon. So this is showing an SED fit. So the SED posterior with the kids photometry, you can see that it's not like it's less well constrained, but still looking pretty nice, pretty good fit. And we still get pretty nice posteriors on all of these parameters, despite the fact that it's only these 9 broadband data points. And it's also somewhat noisier photometry than Cosmos. So this is kind of showing the advantage of having that prior. You can still fit these models to this relatively sparse data and get good results. And here is comparing our photometric redshifts and spectroscopic redshifts for 200,000 galaxies from kids, where there's spectra available, so from DESI, Gamma, SDSS, and a couple of small pencil beam surveys. And on the right-hand side, we're showing our learned population prior, the results where we use that. And on the left-hand side, we're showing the results for a broader prior. So you can see that having the tighter prior on all the parameters, it sort of brings in some of these outliers. You tighten everything up, which is nice and what we would hope would happen. And here's just a couple more results showing some parameter inferences for different subsets of the kids' galaxies that were spectroscopically classified. So things that were classified as like luminous red galaxies, for example, we find they're all very high mass in our posteriors and very low star formation rates, which is what you'd want to see. So that's a nice sanity check. And then obviously we're now lucky to have DP1 with us, and we're working towards being able to do SED fits for all of the galaxies there, which we'll hopefully make available to the LSST community. And yeah, generally looking at, like, for example, model colors for LSST compared to what's actually in the data. And so far, I've been working on setting up some emulators for our SPS model to be able to get LSST magnitudes from the SPS model really quickly. And that's all working well, so that's good. And if you're in LSST desk on this course, I know some people are in both science collaborations or more than 2 even, then we have a project called Project 430 in the desk publication database thing. So feel free to reach out or add yourself to that if you're interested. And a few other future directions that we're thinking about. So in the near term, we want to get everything ready for a DP1, start getting parameter posteriors for all those galaxies. Something I'm interested in doing in the future is taking our population model and asking the question, okay, what part of the whole galaxy population hosts, for example, type 1a supernovae or things like that? And so to do that, you can take the population model, take a bunch of supernova host galaxy photometry, and then learn, okay, what parts of the galaxy population can I slice off, or what parts of the galaxy population are needed to produce that supernova host population. And so that's something I'm interested in working on in the future. And also, I don't know if any of you have seen, if you haven't seen Blast before, this is great, and you should use it. It's a really nice tool that David Jones and Peter McGill and many others developed for getting transient host galaxy photometry and SED fits and things like that. And we're hopefully going to put our model into this in the short to medium term, so we can use it to get parameter inference and redshift inferences for host galaxies, which will be fun. So that's it. Yeah, I'll take any questions, I guess, or thanks for listening to a talk that was mostly not about transients.
Thank you so much. It was super interesting. I think it's very related to transients. We care about their hosts, so for extragalactic transients. So thank you so much. If you have a question for him, Stephen is a postdoc at the Oscar Klein Center at Stockholm University, and he's soon moving to Cambridge. So you can contact him. Thank you so much for attending.